This video is the third in a series about intermolecular attractive forces. If you haven't watched the first one and the second one, you'll want to stop this video, go back, take a look at those first, because this video is going to build on those concepts. When we have intermolecular attractive forces and we're trying to decide whether a substance has a stronger intermolecular attractive force or a weaker intermolecular attractive force, sometimes you're going to run into a circumstance where you have two dipole-dipole substances. So two substances that come up with dipole-dipole as their intermolecular attractive force. And what you want to remember in those circumstances is that the more polar a substance is, the stronger the intermolecular attractive forces will be. In general, more electronegative elements, we know about electronegativity from the periodic table, will lead to more polar substances. So let's look at an example. Let's consider PCl3, PBr3, and PF3. And notice these are very similar molecules. They all have phosphorus as their central atom and a halogen attached to, and three halogens attached to the phosphorus. And so really they all take the same format, and we'll just draw phosphorus trichloride here as an example. They're all trigonal pyramidal molecules, they're all polar molecules, and none of them have NH, FH, or OH bonds. So we know that all of these molecules have dipole-dipole forces between molecules. So when we're asked which molecule has the highest boiling point, and we're looking at these three guys over here, the question becomes, who has the strongest intermolecular attractive force? Well, when we look at chlorine and bromine and fluorine, we know that fluorine is the most electronegative of those three. We know that bromine is the least electronegative of those three. And so, in theory, since they're all attached to phosphorus, we should see phosphorus trichloride as having the strongest intermolecular attractive forces, and phosphorus tribromide as having the weakest. Now keep in mind we're speaking in theory here, based on what we know about electronegativities, based on what we know about intermolecular attractive forces. So the highest boiling point then should be the molecule with the strongest intermolecular attractive forces, and that would be PF3. The molecule with the lowest vapor pressure would be the molecule that has the weakest intermolecular attractive forces. The lowest vapor pressure would be from the strongest intermolecular attractive forces, because remember our discussion of vapor pressure, we have liquid. We're talking about how many particles are in the gas phase. If you have really strong intermolecular attractive forces down here, you don't get very many molecules in the gas phase, and so you have a low vapor pressure. So our lowest vapor pressure will come from the strongest intermolecular attractive forces, so this is also PF3. And then which molecule has the highest sublimation point? Again, PF3. Hey, it's 3 for 3. Let's talk about London forces. These come, as we know, from nonpolar molecules. And if you had three nonpolar molecules that you were trying to decide who has the strongest forces, we want to look at the fact that heavier molecules have more electrons. And the reason that this is important is kind of think about a pillow. And I found this cool pillow on the internet. And you might be thinking of taking a nap right now. But when you take a nap, your head squishes the pillow, right? And you can squish the pillow and condense it really down. You can compress it quite a bit. And you can also squish it to one side or to the other side. So when we think about electrons on a molecule, they're kind of like a pillow, in that we can squish them to one side or the other. Or they might decide to randomly be all on one side of the molecule or another. And so we talk about that ability of the electrons to be moved around as their polarizability. The more electrons you have, the more polarizability you have, and the greater your instantaneous dipole will be when you have two nonpolar molecules coming into close contact. So think about it this way. I've got this molecule and this molecule, and as they get closer to each other, the electrons on this molecule and the electrons on this molecule say, hey, wait a minute, we don't really like each other. And so for a moment in time, this molecule scoots all of its electrons over here. And here's our nucleus in the middle. And what causes to happen then is I get a partial negative buildup on one side of the molecule and a partial positive on the other. Hey, that nonpolar molecule looks kind of polar. Well, it doesn't last, because those electrons will eventually go back to being evenly distributed or being on the other side of the molecule. But the more electrons you have, the bigger this partial negative and this partial positive will be, and the stronger your intermolecular attractive forces will be between those two molecules. So, if we consider CH4, C3H6, and C5H10, all of these are molecules that contain CH and CC bonds. CH and CC bonds we know are all nonpolar, and so all of these are nonpolar molecules. So when we're asked to figure out which has the lowest melting point, we're really looking for the weakest intermolecular attractive forces, the weakest IAFs. And because these are all nonpolar molecules, we're looking for the one with the least number of electrons, or the smallest molecule. So really, here, we're looking for the smallest molecule. And that would be CH4. Who has the highest vapor pressure will also be the smallest molecule with the weakest intermolecular attractive forces. So that's also CH4. And the highest freezing point, now we're looking at molecules that are really strongly attracted to each other. So in this case, we're looking for the strongest intermolecular attractive forces. And so we're looking for the largest molecule of these three because they're all nonpolar. And so that would be C5H10.